You don't actually live in the Milky Way. You live inside something much larger, a family of more than 80 galaxies bound together by gravity, most of whose mass has never been seen. For almost a century, astronomers have been trying to answer a surprisingly simple question. Where does this place end? Every time they think they've found the border, it moves farther away. Tonight, we'll follow that moving boundary, from the first maps of the local group to the invisible halo that may never have a true edge at all. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories are kept alive by hearts as kind and thoughtful as yours. Now, let's begin. In 1936, Edwin Hubble sat down to give a name to the patch of universe we live in, and he counted 11 galaxies. 12, if you were feeling generous about one faint smudge trembling near the limit of what his telescope could pull out of the dark. He wrote the number down. He called it the local group, and for a long time that number felt like the truth. Tonight, we count more than 100. Around 125 confirmed, with a few dozen more still standing trial, waiting to hear whether they belong to us or not. So sit with the size of that gap for just a moment. Not 11, then 13, then 15. 11, then 125. A tenfold jump in the census of our own home. And that leaves us only two ways to explain it. And one of them is quietly unsettling. Either 100 galaxies came drifting into the neighborhood over the last 90 years, sliding in from somewhere else while we weren't looking, or every last one of them was already here the whole time, and we simply could not see them. It's the second one. All of them, already here, already ours, back when Hubble was squinting at his plates and writing down 11. He was standing in the middle of a crowded room in the dark, and he named only the few faces lit by the window. So the first real question of the night isn't how big the local group is. It's why we were blind to most of it for 100 years. And the answer lives inside the tool itself. Hubble was working with photographic plates, sheets of glass coated in a chemical that darkens where light strikes it. You point the telescope, you open the shutter, and you wait. Sometimes for hours, letting the faint light of distant things slowly etch itself into the emulsion. It's patient work. It's beautiful work. But it has a hard floor. If an object is too faint, it never darkens the plate at all. Not after an hour. Not after 10. It leaves no mark, and to the astronomer holding that glass up to the light, it does not exist. The bright ones announce themselves easily. The Milky Way we live inside. Andromeda, our great twin, 2.5 million light-years off, and still faintly visible to the naked eye on a dark night. The two Magellanic clouds slung beneath the southern sky. A scattering of others with just enough glow to burn through. Those were the faces by the window. Everything dimmer than that threshold sat in the same sky, in the same photographs, and stayed perfectly, completely invisible. Now, you could push back here, and you'd be right to. Better telescopes came along, you'd say. Bigger mirrors, sharper detectors. Of course we found more. That's just the machinery improving. And for a while, that's exactly how it went. A galaxy here, a galaxy there, added one at a time as the instruments got hungrier for light. But the number did not creep upward politely. Right around the year 2000, it broke into a run. And it ran because we changed the question entirely. We stopped asking which galaxies are bright enough to see, and started asking a colder, stranger question. Where in the sky are the stars standing just a little too close together? That shift sounds small. It was a revolution. Digital surveys began scanning huge stretches of sky and recording not blurry blobs but individual stars, millions of them, each one a point with a position. And then the computers went looking, not for anything glowing, but for a place where a few hundred faint stars were packed into a patch tighter than random scattering should ever allow. No smudge. No glow. Nothing your eye would ever catch. Just a bump in the statistics, a faint overcrowding that resolves into an entire galaxy hanging over your head on every clear night of your life, one you were never able to see and never will. Think about how eerie that method actually is. You do not spot the galaxy. You prove it must be there. You run the arithmetic on a field of stars. The arithmetic comes back impossible for empty space. And out of that impossibility, a world appears. And the moment we learned that trick, the map didn't nudge. It tripled, then kept climbing. And it is still climbing tonight, right now, as new surveys sift fainter and fainter overcrowdings out of the dark, each one a candidate, each one a maybe. Which drops us straight into the second question, and it's a trap dressed up as an easy one. What does it actually mean to belong to this group at all? Because when you go looking for the edge, there isn't one. No wall, no fence, no line scratched across the black that says the local group stops here and the rest of the universe begins there. Gravity refuses to give us that. It never switches off. It only fades with distance, weaker and weaker, all the way out, never once reaching zero. So the boundary had to be invented, and the one astronomers settled on is honest about what's really going on out there. A galaxy counts as one of us if it is falling toward us, rather than being carried away on the expansion of space itself. Step far enough out, and everything is drifting apart as the universe stretches, thinning into the distance. Come close enough in, and gravity overrules the stretching, and things fall inward instead, toward the shared center of gravity that sits between the Milky Way and Andromeda. That invisible tipping line, the exact place where falling in finally beats drifting away, is the true edge of home. A border made of motion, not matter. And once you draw that border properly, the size lands like a quiet shock. Most of us grew up picturing the local group as the gap between here and Andromeda, 2.5 million light-years. A snug little pocket. The real gravitational reach stretches close to 10 million light-years across, roughly 4 times wider than the tidy diagram in the school book. And I'll be honest with you, that fact got under my skin the first time it landed. The picture I learned this from as a child was already wrong on the day it went to print, and no one had gotten around to telling the mapmaker yet. So look at what we've quietly pulled loose in the dark here. We know why we undercounted our own home for a century. We were counting light, and it happens that most of our neighbors barely give off any. And we know what it truly means to be a member. Not an address, not a spot on a grid, a direction of falling, chosen long ago by gravity, sorting every object out there into the ones sliding toward us and the ones slipping forever away. But notice the word we've been leaning on this entire time without stopping to check it. Faint. We keep calling these hidden galaxies faint, dim, buried in the noise, as if that were a small and gentle thing. It is not. Some of them are so faint that the whole galaxy, every star it owns, all of them summed together into one number, shines with less light than a single ordinary star you could lift a finger and point to right now. And by every rule we thought we understood, that should not be allowed to exist. A galaxy is meant to be billions of suns pouring out light. So what kind of thing holds itself together like a galaxy, orbits like a galaxy, earns the name galaxy, and still burns dimmer than one lonely star lost in the same sky? The answer, when it finally comes, is almost insulting in how simple it sounds. A galaxy can shine dimmer than a single star, because it barely has any stars at all. Take the one that broke the record. Its name is Sege Un, and we found it in 2007, buried in the same kind of statistical overcrowding we talked about a moment ago. It sits about 75,000 light-years away, close by cosmic standards, practically in our backyard. And when astronomers finally counted its stars, they found a few hundred. Not a few 100 billion, like the Milky Way. A few hundred. A number you could almost reach by counting the people in a small theater. And not one of those few hundred is a brilliant blue giant, the kind of star that lights up a normal galaxy from across the universe. They're old, small, dim red embers, most of them, the quiet survivors of a fire that stopped burning almost as soon as it started. Add every one of them together, pool all their light into a single glow, and the whole galaxy still shines fainter than one bright red giant star you could pick out on your own tonight. So that seems to settle it. Segue uno is a wisp, a scrap, a handful of leftover stars barely worth the name galaxy. And that is exactly the moment the floor gives way. Because when you watch those few hundred stars carefully, tracking how fast they drift, they are moving all wrong. They're orbiting far too quickly. A few hundred faint stars, by their own gravity, could never whip their members around at the speeds we measure. Stars moving that fast should simply fly apart and scatter into the dark, and yet Segue One holds together, tight and stable, as it has for billions of years. Something is gripping it. Something heavy. When you add up how much mass it takes to hold those stars on their fast little orbits, the number lands near 600,000 times the mass of the Sun. But the stars themselves, all of them together, account for only a few hundred suns worth of matter. So run the subtraction gently and let it sit. More than 99.9% of Segue One is something you cannot see, something that gives off no light of any kind. We have a name for the ratio, and it's stark. In a normal galaxy like ours, for every unit of light, there's roughly 10 units of total mass. Some visible, some dark, a manageable mix. In Segue One, for every unit of light, there are somewhere between 1,000 and 3,000 units of mass. It is, by that measure, the darkest object we have ever found. A galaxy that is barely made of stars at all, and almost entirely made of the invisible. And this is the strange gift hidden inside the faintness. You might think the giant galaxies, the grand bright spirals, would be the best places to study this invisible mass. They're the opposite. In a big galaxy, the visible stars and the invisible matter are tangled together so thoroughly that pulling them apart, weighing one without the other, is maddeningly hard. The light gets in the way of seeing the dark. But in Segway 1, there is almost no light to get in the way. There's so little ordinary matter that what you're left measuring is nearly pure invisible mass, laid bare, with nothing to hide behind. The darkest galaxy in the sky turns out to be the clearest window we have into whatever that dark stuff actually is. The thing hardest to see becomes the thing easiest to study. There's a small human story tucked into all of this, and I keep turning it over. Segway 1 has a cousin called Willman 1, and it carries that name because a young astronomer named Beth Willman pulled it out of the data in 2005, sifting through millions of points of light for a shadow that shouldn't have been there. And for years afterward, people argued about it. Was it even a galaxy at all, or just a battered old star cluster wearing a disguise? These objects live so close to the edge of being nothing that we could barely agree they were something. The faintest things we find are always the last ones we're willing to believe in. So you'd be forgiven for thinking that is a niche pursuit. A few astronomers chasing the dimmest smudges in the sky for the thrill of a record. It is nothing of the kind. Our best theory of the universe, the one built on cold, dark matter, makes a hard prediction. A galaxy the size of ours should be surrounded by hundreds, maybe thousands, of these small, dark clumps, each one a potential home for a scrap of stars. For decades, we could only find a dozen or two. The prediction said hundreds. Reality showed us 20. That gap even earned a name, the missing satellites problem, and it hung over cosmology like an unpaid debt, a sign that maybe our whole picture of the universe's hidden skeleton was wrong. And then the ultra-faint galaxies began to appear. One, then another, then a steady trickle as the surveys grew sharper, each new ghost nudging the count upward toward the number the theory had demanded all along. So when we find a galaxy dimmer than a single star, we are not collecting oddities. We are checking whether the invisible scaffolding the entire universe hangs on is really there. And every faint smudge we drag out of the noise is a small vote for or against the way we think everything is built. I find something quietly humbling in the shape of that. The brightest, most photographed galaxies, the ones on every poster, told us the least about what the universe is actually made of. The nearly invisible ones, the overlooked scraps we almost refused to count, told us the most. But look closely at what we just did to Segway 1. We weighed it. We found 600,000 suns of mass with almost nothing visible to show for it, wrapped around a few hundred stars. If a scrap of a galaxy can be buried that deep in invisible weight, then the obvious question is the one pointed straight back at us. How much of that same unseen mass is wrapped around the Milky Way, around you, right now? And how far past the last visible star does it actually reach? The mass around you isn't a little extra. It's most of everything you belong to. Start with what you already know by heart. The Milky Way, the way it looks in every photograph, is a glowing pinwheel of a few 100 billion stars. A bright, flat disk, about 100,000 light-years across. That's the galaxy of the posters. The one we name, the one we live in, the one we point to. And it is real, but it is only the ember at the center of something enormously larger and almost entirely unseen. Around that bright disk sits a vast sphere of dark matter, the same invisible stuff that outweighed the stars 1,000 to 1 in that tiny ghost galaxy we just weighed. Only here it wraps our whole home. And it reaches out staggeringly far. The glowing part of our galaxy stops around 50,000 light-years from the center. The dark halo keeps going out to something like 1,000,000. Roughly 20 times farther than anything that shines. Let me put that in your hand. Shrink the visible Milky Way, all those hundreds of billions of stars, down to the size of a dinner plate on your table, about 10 inches wide, 25 centimeters. On that scale, the dark matter halo around it wouldn't be a slightly bigger plate. It would be a sphere the size of a small house, with the entire visible galaxy sitting as one bright dish at the very center of an empty-looking room. And now the part that quietly rearranges where you think you are. You are not looking up at this halo. You are not observing it from outside, the way you'd study a photograph. You are inside it. Deep inside it, near the very middle. It isn't a structure hanging somewhere in the sky. It's in every direction at once, over your head and beneath your feet and past every horizon. A sphere of invisible mass you have been sitting at the heart of for your entire life, without a single sensation to tell you it's there. So, what is it? And this is where honesty matters more than confidence. We don't know. We can map its shape. We've traced that it's not a perfect ball, but a slightly squashed, gently tilting sphere, leaning more as you move outward. We can measure how far it reaches and how much it weighs. What we cannot yet do is tell you what it's made of. No one has ever held a piece of it, or caught it in a detector, or named the particle. We know this thing entirely by its pull, and by nothing else. Which raises a fair challenge. If you can't see it, catch it, or name it, how do you know how big it is at all? The answer is that we watch what it drags. Far out beyond the visible edge, there are satellites, small companion galaxies, looping around us on enormous slow orbits. One of them, Leo the First, hangs about 800,000 light-years out, and it is still firmly on a leash, still bound, still circling. For our gravity to reach a thing that far and hold it, there has to be mass out there doing the holding, mass we cannot see, filling the space the stars have long since abandoned. And there are the streams. When one of those little galaxies wanders too close, we tear it apart, and its stars unspool into a long, thin ribbon looping around the sky. Those ribbons drape themselves along the shape of our gravity like dye poured into a current, showing us the invisible flow they're riding. Trace enough of them, and the outline of the dark halo slowly appears, the shape of a thing drawn entirely by what it moves. So our home is 20 times wider than it looks, and most of it is dark. Fine. But that immediately sharpens a question we've been circling since the very start of tonight. If our halo reaches out 1,000,000 light-years in every direction, where exactly does it end? And what happens when it meets the one next door? Because Andromeda is out there, 2.5 million light-years away, and it is not a smaller thing than us. It's our equal, maybe our better, wrapped in a dark halo of its very own, roughly as vast as ours. So picture the two of us, each buried at the center of a sphere reaching outward about 1,000,000 light-years, separated by 2.5 million. The math is close enough to make you lean in. Our reach, plus its reach, very nearly closes the gap between us. And the faint gas tells an even more intimate story. Each galaxy is wrapped not just in dark matter, but in a thin, warm haze of gas, a kind of atmosphere stretching far past the stars. Careful surveys of Andromeda's atmosphere find it billowing out toward us, reaching something close to halfway across the entire gap. If ours does the same, and it very likely does, then the two atmospheres may already be touching in the middle of that darkness, the faintest breath of one brushing the faintest breath of the other, right now, tonight. I want to be careful here, because this is where certainty runs out. Whether the deep, dark halos truly overlap or merely reach toward each other is still unsettled. The standard picture says the two great spheres began well apart and have been closing slowly ever since. But the outer edges, the thin gas, the faintest reach of each, those may have met long ago, quietly, with no light and no violence to mark the moment. And there's something in that I keep coming back to. We spend so much effort naming the sharp, dramatic moments. The collision, the merger, the date 4 billion years from now. But the real touching, if it's happening, isn't sharp at all. It's a slow leaning together of two nearly empty atmospheres across an ocean of dark, so gentle that no one could ever point to the day it began. Which leaves us holding a strange new thought as we go. We've always filed the meeting of our galaxy and Andromeda safely in the distant future, a headline for a world without us in it. But if the outermost edges of the two are already resting against each other, then that future event isn't purely in the future. Some first, faint part of it may already be underway. So when we say the collision is coming, we should probably ask a harder question first. When did it actually start? For most of a century, the ending was already written. Since 1912, we've known Andromeda is coming toward us, sliding closer at about 70 miles a second, 110 kilometers every second, never slowing. And by a dozen years ago, the story felt settled down to the timing. In roughly 4.5 billion years, the two great spirals would fall together, tear through each other, and slowly merge into a single, smooth, elliptical galaxy. It had a name, Milkomeda. Our sun flung onto some strange new orbit, the night sky rebuilt from scratch. It was in the textbooks. It played on planetarium domes. It was, as far as anyone taught, a fact. Then, in the late spring of 2025, a team of astronomers erased it. And what they wrote in its place wasn't a different ending. It was a question mark. Here's what they actually did. Led by Till Sawala in Helsinki, with colleagues in Durham and Toulouse, they took the sharpest measurements we have, more than a decade of Hubble tracking and the exquisite star mapping of the Gaia mission, and they ran the encounter forward more than 100,000 times. Not once, with a single best guess for every number. 100,000 times, letting each uncertain measurement wander across its full, honest range. And that one change in method, taking our own doubts seriously, cracked the whole thing open. The old prediction had been built on a kind of quiet confidence. Take the most likely value for every quantity, feed them in, get one clean answer. Collision, certain. But when you let the numbers breathe, when you admit you don't know Andromeda's motion perfectly and you let it range over everything the data allows, the single certain future scatters into a whole spray of possible ones. Some of them collide. Some of them sail right past. And then they added a player everyone had been leaving out. The Large Magellanic Cloud. It carries only about 15% of the Milky Way's mass, a junior partner slung beneath our southern sky. Small enough to ignore, which is exactly what earlier studies did. But it doesn't pull us toward Andromeda. It pulls us sideways, off the shared orbital plane, nudging our whole galaxy a little out of the line of fire. Andromeda's own big companion, the Triangulum Galaxy, tugs the other way, adding to the approach. Two small hands on the wheel, pushing in opposite directions. When all of it was added together, the number that came out was almost unbelievable for how ordinary it sounds. Roughly a coin flip. About a 50-50 chance the two galaxies merge at all within the next 10 billion years. And a direct, head-on crash in the next 4 to 5 billion years. The very scenario we'd been teaching as destiny came out at around 2%. I'll admit, there's something strange and almost tender in that result. The astronomer who led the work has said he expected the opposite, that he went in bracing for the collision to hold, and was genuinely surprised when the certainty dissolved in his hands. We so rarely get to watch a fact we grew up with turn back into a question. The future we had quietly sentenced our galaxy to, the death and rebirth 4 billion years out, got unlocked. Left open again. Now, hold this against what we found a moment ago. The faint outer atmospheres of the two galaxies may already be brushing across the dark. Both things are true at once, and they don't contradict each other. The gentlest edges can be in contact, while the two bright hearts still have a coin flip's chance of never truly falling together. In about half the simulated futures, they swing past each other at 500,000 light-years or nearer, 5 times the width of the Milky Way, close enough to feel, and then maybe drift apart for a long time before anything more happens, or maybe nothing more happens at all. So why can't we just settle it? We've known the approach for over a century. Why is the outcome still a shrug? And the answer lives in one brutal little measurement. The motion toward us is the easy part. Light from something rushing at you gets crowded toward the blue, and we read that shift straight off, the way we have since 1912. But whether Andromeda scores a bullseye or slips past depends almost entirely on its sideways motion. Its drift across our line of sight. And that is the hardest thing in the sky to measure. Think of a car far down a long straight road at night, headlights growing. You can tell instantly that it's coming closer. What you cannot tell, not until it's nearly on top of you, is whether it's aimed exactly at you or will pass a few feet to your left. That tiny sideways drift is almost invisible at a distance, and yet it's the only thing that decides whether you're hit. Now put that car 2.5 million light-years away, and let its sideways shift be so small that watching for it means tracking Andromeda's faint creep against even more distant galaxies for over a decade. That's the number we're fighting for. And the uncertainty still left in it is wide enough that the answer swings from near certain collision to clean miss. There's a kind of integrity in where they left it. They didn't reach for doom, and they didn't reach for rescue. They said, in plain terms, that the fate of our galaxy is genuinely open, and then they let it stay open. A science willing to walk back its own most famous prediction, the moment the data leans that way, is a science you can trust with the quiet hours. But notice the thread every single one of those 100,000 futures hangs from. They all begin with knowing where Andromeda is. How far, exactly? And that distance, the 2.5 million light-years we've been saying all night as if it were carved in stone, has one of the wildest histories in all of astronomy. There was a night when that number doubled, when the entire universe, in a single announcement, became twice as large as everyone had thought the day before. So before we go any further out, we have to answer the question underneath all the others. How do you measure the distance to a place you can never visit, from inside a house whose walls you can never step past? You don't measure the distance at all. You measure how bright something looks, and you let brightness give the distance away. The idea underneath it is one you already use without naming it. A light looks dimmer the farther away it sits. A candle across a room, a street lamp down the block, a porch light on a distant hill, each fainter than the last, purely because of distance. So imagine you knew, for certain, that a particular bulb was exactly 100 watts. Then its faintness would stop being a mystery and start being a ruler. The dimmer it looked, the farther you'd know it had to be. The entire problem of measuring the universe collapses into a single question. Where in the sky can you find a light whose true brightness you already know? For a long time, we had no such light. And then, in 1912, a woman at the Harvard Observatory found one. Her name was Henrietta Swan Leavitt, and she was one of the so-called computers, the underpaid women hired to catalog stars by hand from photographic plates, one faint point at a time. She was studying the small Magellanic Cloud, a dense swarm of stars all sitting at roughly the same distance from us. And scattered through it were Cepheids, a peculiar kind of star that doesn't burn steadily. It pulses. It physically swells and shrinks, brightening and fading on a strict, repeating beat, some over a few days, some over many weeks. What Leavitt noticed changed everything, and it was almost unbelievably simple. The Cepheids with the slower beat were always the brighter ones. And because every star she was looking at sat at the same distance, that difference in brightness couldn't be a trick of nearness. It was real. The rhythm of the star was telling her its true output. Time the pulse, and you know the wattage. That was the missing light. A Cepheid arrives pre-labeled. Clock its beat. Read its true brightness off Leavitt's law, then compare that to how faint it actually looks in your telescope. And the gap between the two hands, you the distance. A pulsing star had become a ruler you could carry clear across the cosmos. Just over a decade later, Edwin Hubble picked up that ruler and pointed it at the one object that had haunted astronomy for a generation. The Andromeda Nebula. A faint spiral smudge that no one could agree about. Was it a cloud of gas inside our own Milky Way, or something impossibly far beyond it? Hubble found a single Cepheid inside that smudge, timed its beat, read its true brightness, and measured a distance so enormous it ended the argument on the spot. Andromeda was not part of us. It was a separate galaxy, a whole island of 100 billion stars, unthinkably far away. That was the night our galaxy stopped being the universe and became one address in it. We always say Hubble measured Andromeda, but the ruler in his hand was hers. Leavitt had died in 1921, before Hubble's result, before anyone grasped what her little pattern would unlock, before her name was anywhere near it. For decades, the credit drifted toward the men who calibrated and applied her method, and the woman who handed us the yardstick for the entire cosmos was very nearly left off the label. The measurement that told us how big everything is came from someone the field almost forgot to thank. So by the 1920s, the distance to Andromeda felt solid. Somewhere around 900,000 light-years. That number sat in the textbooks for a generation. And then, in 1952, at a meeting in Rome, Walter Baade stood up and told the room the ruler had been broken the whole time. His discovery had an almost unbelievable origin. During the war, the city of Los Angeles ran blackouts, and the darkened sky over the observatory above it turned unusually clear and deep. In that wartime dark, Baade could finally resolve individual stars in the crowded heart of Andromeda that no one had separated before. And studying them, he realized there were two distinct families of Cepheids, not one, each pulsing to a different true brightness. Everyone, Leavitt and Hubble included, had been using a single law for both. The fainter family had been quietly making galaxies look closer than they really were. Correct that one hidden mistake, and Andromeda didn't shift a little. It leapt from 900,000 light-years to roughly 2 million in a single afternoon. And not Andromeda alone. Every galaxy measured with that ruler, everywhere in the sky, moved outward by the same factor. The whole universe, in one meeting, became twice as large as it had been the day before. Stay with how strange that afternoon must have felt. Every distance in every textbook, wrong by half, all at once. Not through anyone's carelessness, but because a single quiet assumption that all these pulsing stars were the same had been holding the entire ladder together. The moment it gave way, everything grew. Today, the number has settled, refined yet again since Baade, to about 2.5 million light-years. And the reason we trust it now is that the ladder is anchored at the very bottom by something completely direct. The Gaia mission watches nearby stars appear to shift, just slightly, as the Earth swings from one side of its orbit to the other, the same way a nearby object seems to jump against the background when you look at it first with one eye, then the other. That tiny shift gives a distance with no assumptions at all, and that rock-solid first rung calibrates the Cepheids, which in turn reach out to the galaxies. Every distance we've spoken tonight rests, in the end, on that first honest step. So the ruler is finally sound. Cross-checked, anchored, trustworthy at last. And when astronomers took that trusted ruler and laid it across the whole local group, measuring every member, the map that came back was not the one anyone had pictured. Not a loose, democratic scattering of 100 equal galaxies drifting side by side. Something with a shape. Something with a center of gravity, and a crowd of the captured. Nearly every one of those 100 galaxies, it turned out, answers to just two masters. And the question that leaves us is why our neighborhood is not a community at all, but a pair of empires. Our neighborhood is not a gathering of equals. It's a system with two centers of power, and almost everything else in it is a subject. The two are the Milky Way and Andromeda, and they really are a matched pair. Close cousins, near enough in mass to be called twins, each a great spiral holding a few 100 billion stars, each wrapped in one of those vast dark halos we walked through earlier. Between them, these two hold the overwhelming majority of everything the local group is made of, somewhere between 3 and 5 trillion times the mass of the Sun, Everyone else, the whole crowd of 100 smaller galaxies, splits the leftovers. But twins are never quite identical, and the differences here are telling. Andromeda carries about 500 globular clusters, dense ancient knots of stars, roughly 3 times as many as we have. Its disk is broader. Its history looks rougher, marked by signs of a major collision in its past, while our own galaxy has stayed strangely, almost suspiciously calm. Andromeda is the scarred, well-traveled sibling. We are the quiet one who mostly stayed home. So the natural question is the one any two rivals invite. Which of them is actually the heavyweight? And this is where I have to be straight with you, because the answer keeps moving. For most of the last century, Andromeda looked like the clear champion, brighter and richer and larger. Then, as we learned to weigh the dark halos instead of just counting the light, the gap narrowed, and some measurements brought the two nearly even, or even tilted the crown toward us. Right now, their mass estimates overlap so much that we honestly cannot say for certain which one leads. The single best-studied pair of galaxies in the universe, and we still can't reliably tell you who's bigger. Now, if you have two roughly equal giants, something strange happens to the center of the whole system. Everything in the local group, every dwarf, every stream, the sun, you, is falling toward the shared center of mass of these two. The balance point, the place all that gravity averages out to. And with two nearly equal masses, that balance point doesn't sit inside either galaxy. It floats in the empty space between them, out in the dark of intergalactic space, roughly 1,000,000 light-years from each. Let that settle for a moment, because it's stranger than it first sounds. The true center of everything we belong to, the point our entire cosmic nation orbits, is a spot where nothing is. No star marks it. No world sits on it. It's a throne in the middle of the void, and no one is on it. I keep circling back to how much we want there to be a somewhere at the heart of home, a capital, a place to point at. And the honest map hands us an empty point in the darkness instead, and tells us that this nothing is what holds all of us together. Around that empty throne, the subjects arrange themselves. Nearly every one of the 100 smaller galaxies is bound to one giant or the other, a satellite of the Milky Way or a satellite of Andromeda, held on a long, slow orbit by a halo it cannot escape. And they don't spread themselves evenly. Curiously, many of the dwarfs prefer the space between the two giants, clustering in that middle ground, as if drawn toward the tension between the two great poles rather than away from it. Most of these subjects are tiny, the faint ghosts we met before. But one of them is large enough to sit awkwardly between subject and rival. Triangulum or M33. It's a real spiral galaxy in its own right, the third largest thing in the local group, carrying about 1/10 the mass of Andromeda, the same ratio our own large Magellanic Cloud has to us. Big enough to be a minor power, not big enough to be free. And M33's story is genuinely unsettled. It almost certainly belongs to Andromeda now, caught in that larger halo. But how long has it been there? When astronomers run its motion backward in time, the leading answer right now is that M33 may be on its first fall inward, arriving rather than orbiting, a newcomer to Andromeda's court rather than an ancient member of it. A galaxy we assumed had always been there may, in fact, be a recent arrival, still descending. This is the real drama hidden under the tidy word satellite. A galaxy caught between two empires is not settled. It's in a tug of war. Andromeda pulls M33 one way. The distant Milky Way tugs faintly from the other, and the smaller galaxy's entire future depends on which halo wins the argument, which throat of gravity finally swallows it. For a dwarf, membership isn't an honor. It's a sentence. The two giants aren't neighbors sharing a fence. They're slowly dividing the spoils. And once you see the arrangement that way, a colder realization follows. Being captured by a giant is not the end of the story for these small galaxies. It's the beginning of a much longer, quieter violence. Because the giants don't simply hold their captives. Over time, they take them apart. We know this isn't a guess, and we don't have to look at Andromeda to prove it. We can look straight up tonight at our own sky. One of the Milky Way's own captured galaxies is being pulled apart by us at this very moment, its stars unraveling from a compact little body into a long ribbon that has already been stretched most of the way around the entire sky. It has a name, and it was hiding in plain sight for longer than it had any right to. So the question that pulls us onward is a hard one to sit with. What does it actually look like when a galaxy is being eaten alive? Look toward the constellation Sagittarius tonight, low in the southern sky, and you are looking at a death in progress. There is a galaxy dying there right now, being pulled apart star by star, and we are the ones pulling. Its name is the Sagittarius dwarf, and for a small galaxy it was astonishingly hard to find. We didn't confirm it until 1994, which is strange because it is enormous in our sky, stretched about 20 degrees from end to end, the second largest structure up there after the band of the Milky Way itself. The reason we missed it for so long is almost embarrassing. It sits directly behind the crowded, glowing center of our own galaxy, roughly 80,000 light-years away, buried behind so much dust and so many foreground stars that you cannot simply see it. The team that found it didn't spot it by its light at all. They found it by motion. Scattered among the sea of Milky Way stars was a group all drifting together at the same odd speed, marching in step, out of rhythm with everything around them. A whole galaxy, betrayed not by how it looked but by how it moved. The most dramatic event in our galaxy's recent life had been hiding behind the brightest thing we ever look at. So how does a galaxy get torn into a ribbon? The mechanism is patient and it never lets go. As the dwarf orbits us, the near side of it feels our gravity a little more strongly than the far side, and that difference alone begins to stretch it. But the deeper pull is orbital. The stars on the inner edge, closer to us, orbit slightly faster and pull ahead. The stars on the outer edge orbit slightly slower and fall behind. Over many loops, the dwarf stops being a compact blob and smears itself out along its own path, its stars unspooling forward and backward into a long, thin stream. It's the same kind of tidal stretching that raises the ocean under the moon, only here it acts on an entire galaxy, and it doesn't relax. And the result is written across the whole sky. The stars stripped from Sagittarius now form a vast pale band that wraps more than a full loop around us, over the top of the galaxy and back underneath, a complete circle of stolen stars. When you trace that stream, you are following the unwound body of a galaxy we have been slowly swallowing for billions of years. Its remains are already all around us, threaded through the halo, mixed into the sky we call our own. But this dwarf did not go quietly, and it left marks on us in return. On its looping path, Sagittarius has punched straight through the disk of the Milky Way at least 3 times. And each time it did, It rang our galaxy like a struck bell. When the Gaia mission mapped the motions of millions of nearby stars, it found them rippling, rising and falling in a faint, coordinated wave, the aftershock of the last time this small galaxy crashed through our plane. We can still feel it moving through us. Those crossings did something even more consequential than ripples. Every time Sagittarius plunged through the disk, it compressed the gas it passed through and squeezed clouds of it into new stars. The timing lines up. Bursts of star formation in our galaxy match the moments this dwarf came through, roughly 6 billion years ago, then around 2, then near 1. Each passage, a wave of new suns lighting up in its wake. And this is where the story turns and looks straight back at us. The sun formed about 4.5 billion years ago. Some researchers have proposed that one of these Sagittarius passages, close to that time, may have helped trigger the very burst of star formation that gave birth to the sun. I want to be careful and call this what it is, a live hypothesis, not a settled fact. But hold the shape of it for a moment anyway. The same slow violence that is tearing that galaxy apart tonight may be the reason there is a sun at all. The reason there is an Earth, and warmth, and you, lying here in the dark? Cannibalism and creation, possibly, as the same act. There is a strange tenderness in that, if you let it in. We are unmistakably the predator here. We caught this galaxy, we are dismantling it, and its stars are becoming ours. And yet we are also the ones who finally noticed it, who pulled its hidden shape out of the noise and gave it a name, after it spent nearly all of human history unseen behind our own light. And Sagittarius is not even our first meal. Long before it, roughly 10 billion years ago, our young galaxy swallowed something far bigger, an entire galaxy we now call Gaia Enceladus. That one is fully digested. Its stars no longer form a stream you can point to, but they are still here, moving through the halo on long stretched-out orbits that give them away, foreign stars folded so completely into us that only their motion remembers where they came from. A large part of what we call the Milky Way is other galaxies, eaten and absorbed, their names invented by us long after they stopped existing on their own. So we have been sitting comfortably at the top of this food chain all night, the giant that captures and consumes. The eater. But there is a move left in this that undoes that comfort completely. Because if you pull back one more level, past the Milky Way, past Andromeda, past the whole crowd of captured dwarfs, and look at the entire local group as a single object, you find that it is not sitting still at the center of anything. It is falling. All of it, together, moving fast through the dark towards something we have not named yet. And not one of us, on this quiet earth, can feel a thing. We are moving at about 390 miles a second. Not the Earth around the sun, not the sun around the galaxy, but the entire local group as one object, the whole thing, racing through the universe at 630 kilometers every second. And you feel none of it. You feel, if anything, perfectly still. Let me anchor that speed to something you can hold. At that rate, we cover about 63 light-years every single year. The entire distance to Andromeda, the 2.5 million light-years we've been crossing in our minds all night, we could physically cover in around 40,000 years, which is roughly the age of the oldest paintings on the oldest cave walls. Since the first human pressed a hand to stone and blew pigment around it, we have moved far enough to nearly reach our sister galaxy. and in all that motion, no one has ever felt a breath of wind. That absence of sensation is not a failure of our senses. It's the deepest clue in the whole story. You don't feel this motion because everything around you is falling with you at exactly the same rate. The earth, the sun, every star you can see, the ground under your bed, all of it is dropping through space together, in perfect step. And when everything falls at once, there is nothing to fall against. It's the same reason someone in a dropping elevator floats for a moment, weightless, unable to feel the fall at all until something stops it. We are in that elevator, and nothing is going to stop it. So here is the real puzzle. If you cannot feel the motion, and everything nearby is moving with you, then how could anyone possibly measure it? What do you clock your speed against when your speedometer, your road, and your whole reference frame are all racing along beside you? The answer is one of the most quietly beautiful measurements we've ever made. We measure ourselves against the light of the beginning. The oldest light in existence, the faint afterglow left over from the birth of the universe, fills the entire sky in every direction, almost perfectly even. Almost. Because we are moving, the sky ahead of us, the direction we're racing toward, looks very slightly warmer, its light nudged a little higher in energy. And the sky behind us looks very slightly cooler. Picture driving through steady rain. More drops strike the front windshield than the back, harder. And from that difference alone, blindfolded to the road, you could tell which way you were headed and how fast. The ancient light is our steady rain, arriving from all of time, and it strikes us a touch warmer straight ahead. From that faint imbalance, we read our true speed through the universe itself. And once we knew our speed and heading, the next question wrote itself. What is pulling us? Part of the answer is Virgo, a great cluster of over 1,000 galaxies tugging us toward it. But most of the pull comes from something farther and heavier, a colossal concentration of mass in the direction of the constellations Hydra and Centaurus, dragging our entire supercluster toward it. We gave it a blunt, honest name, the Great Attractor. And the Great Attractor comes with a cruel little twist. We cannot see it. It sits almost directly behind the crowded, dusty disk of our own Milky Way, in a region astronomers simply call the zone of avoidance because our galaxy's own glow and grime block the view of whatever lies beyond. The single largest thing pulling on us is hidden by the very galaxy it's pulling. We are being drawn toward a place we've never clearly seen, obscured by our own body. You'd think then that our fate is sealed. A vast mass ahead, an entire supercluster in motion, all of us sliding steadily toward that hidden basin. But something enormous stands in the way, and it isn't a wall of matter. It's the expansion of space itself, and it's speeding up. On these giant scales, the stretching of the universe is accelerating, and it pulls the Great Attractor away from us faster than our fall carries us toward it. So we are falling toward a destination we will never reach. Racing at 390 miles a second toward a place that is receding faster than we can close the gap. The fall is real, and it is endless, and it never lands. A motion with no arrival. And that single fact quietly resizes our entire home. Because if the expanding universe will always pull the Great Attractor beyond our reach, and Virgo beyond our reach, and every supercluster beyond our reach, then the largest thing we will ever truly stay bound to, the biggest structure we get to keep forever, is the local group. This small crowd of 100 galaxies is not a way station on the road to somewhere grander. It is the whole of our permanent address. Everything beyond it is already leaving and will never come back. There is a strange peace hidden in all of this, and it took me a while to find it. We cannot feel our own tremendous speed, and the light from the very beginning of time is the only mirror patient enough to show it to us. We are held in a fall so gentle and so completely shared that it is indistinguishable from rest. Moving faster than we can imagine, toward a place we'll never see, and it feels, from inside, exactly like lying perfectly still. But a thing that is bound together forever must have an edge. A line where belonging to us stops, and the endless leaving away begins. Somewhere out in that darkness there is a surface, a boundary, marking the outermost reach of everything we will ever keep. It is not made of matter. Nothing sits on it. And finding exactly where it lies means asking what the true edge of home is made of when it's made of almost nothing at all. The most important border in your existence is one you could drift straight through without feeling anything at all. No wall marks it. No shore, no fence, no line of light. And yet on one side of it, you belong to us forever. On the other, you are gone for good. To find that border, look at what happens to any galaxy sitting near the edge of our territory. Two things are pulling on it at once, in opposite directions. Our combined gravity, all those trillions of suns of mass, is drawing it inward toward us. And the expansion of space itself is carrying it outward, away, stretching the distance between us with every passing moment. Every galaxy out there lives inside that tug of war, gravity pulling in, expansion carrying off. Close to us, gravity wins easily. A nearby galaxy is reeled in, held, kept. Far away, expansion wins completely, and the galaxy is swept off into the widening dark, never to return. But somewhere between those two, there has to be a shell where the two exactly cancel. A distance where the inward pull of our gravity precisely matches the outward carry of expanding space. Think of walking up an escalator that's moving down, matching your steps exactly to its speed. You climb, and you stay in one place, neither rising nor sinking. A galaxy on that special shell is doing the same thing. It is falling toward us at precisely the rate space is carrying it away, so its distance from us never changes. It hangs there, motionless relative to us, held perfectly still by the balance of two enormous forces working against each other. That shell of perfect balance is the true edge of home. Astronomers call it the zero-velocity surface because a galaxy sitting on it has zero velocity toward us or away. Everything inside it is falling inward, bound to us, part of the family. Everything outside it is riding the expansion away, already lost. This is the real boundary of the local group. Not the edge of the light, not the edge of the stars, but the edge of what our gravity can still hold on to against the widening of the universe. And it lies farther out than the visible members ever suggested. The best estimates place this balance shell somewhere around 3 to 5 million light-years from the center, in every direction. The exact number is still argued over, because it depends on how much the local group actually weighs, and that is a question we haven't fully settled. But the shape of the answer is clear. Our true home is a sphere several million light-years across, and its surface is drawn not by anything you could touch, but by a balance of pulls. Which is what makes this border so strange to hold in the mind. It is made of nothing. There is no membrane out there, no ring of matter, no marker of any kind. A traveler crossing it outward would see empty space ahead and empty space behind and feel not the faintest change. And yet that crossing would be the most final thing that could ever happen to them. Inside, you are part of a structure that will hold together for the rest of time. One step past, and the expanding universe owns you, and it will carry you away forever, and there is no coming back. We expect our borders to be made of something. A coastline, a wall, a river, a fence, some solid thing that says here and no farther. The deepest boundary of everything we belong to is made of no such thing. It is a place in the dark where two invisible forces fall silent against each other, and that silence is the entire border. There is a quiet in that I did not expect to find. A galaxy poised exactly on the line is not struggling. It is simply held, suspended between being kept and being released, neither approaching nor departing, resting in the balance. The most consequential edge in the cosmos turns out to be a place of perfect stillness. But the line does not stay where it is. Over the vast reach of cosmic time, that border moves, and it moves inward. Because the expansion of space is not steady. It is accelerating, driven by dark energy, growing stronger against gravity as the eons pass. And as expansion strengthens, the point where it overpowers our pull creeps closer to home. The balance shell tightens, slowly, like a noose drawn in over billions of years. Galaxies that are barely bound to us today will, in the far future, find themselves on the wrong side of that shrinking line and drift away one by one. The border made of nothing is quietly closing in, and what it encloses grows smaller with time, until in the end it holds only the innermost core of everything we ever had. Home is not just finite. It is contracting. For now, though, the shell sits far out there, a few million light-years off, holding our 100 galaxies inside it. And that raises a gentle question about the other side. If you cross that silent border outward, into the space our gravity has already surrendered, what would you find drifting there? Because the region just beyond the line is not empty. There are galaxies out there, small, lonely ones and little clusters, hovering just past the edge of rescue. And some of them have been kept so untouched, so far from everything, that they may be stranger than anything we hold inside. Cross that silent border, step just outside the reach of everything that holds us, and the first thing you meet is a line of galaxies walking in single file. 5 small ones, strung out almost perfectly straight, like beads on a thread pulled taut across the dark. We call them the NGC 3109 Association, and they are the nearest distinct group of galaxies to our own, sitting about 4.5 million light-years away. And they are standing right in the doorway. That distance places them almost exactly on the zero-velocity surface, the balance shell we just drew, the line between what falls back to us and what drifts away forever. Which means astronomers genuinely cannot agree on whether they belong to us or not. Some models pull them gently inward, still ours. Others let them slip outward with the expansion, already leaving. A whole little chain of galaxies, caught in the threshold, neither fully in nor fully out. And there is a stranger possibility for how they got there. Not all of the galaxies drifting just beyond the fence are outsiders who never came near. Some of them, the models suggest, may be former members. Galaxies that long ago fell inward toward the local group, swung once through its crowded interior, and were flung back out the other side by the slingshot of all that gravity, like a stone whipped around and released. They touched home once and were cast out, and now they coast forever in the dark just past the edge. We call them backsplash galaxies. Not strangers beyond the wall. Exile. But past that threshold, farther out and truly alone, live the real hermits. Isolated dwarf galaxies with names like Cetus, Tucana, Aquarius, scattered through the emptiness, far from either giant, far from each other, far from anything large enough to bother them. And that isolation is exactly what makes them priceless. Every galaxy we've studied close to home has been handled. Stretched, stripped, torn, reshaped by the pull of the Milky Way or Andromeda, the way Sagittarius is being unwound right now. These distant hermits have been touched by nothing. They still hold their original shape, their original gas, whatever rhythm of star formation they were born with, preserved across billions of years because no giant ever came close enough to disturb them. There is something in that I find quietly moving. The ones left completely alone are the ones that stayed whole. We can never rewind our own galaxy to see what it would have been without all the collisions, the swallowed dwarfs, the endless reshaping. That history is written into us permanently. But these untouched hermits are the closest thing we have to a photograph of what a galaxy looks like when the universe simply leaves it be. They are the control group for an experiment we could never run on ourselves. And they hold a puzzle we haven't solved. A few of these lonely dwarfs, Cetus and Tucana among them, are quiet and gas-poor, their star formation long since ended, more or less dead. Which should not happen. A dwarf gets its gas stripped and its fires snuffed out when a giant harasses it, and no giant ever came near these two. Something ended them from the inside, or something reached them that we haven't identified. And we still don't fully know what silenced galaxies that nothing was supposed to have touched. Widen the view, and our hermits turn out to have neighbors of their own. Beyond the edge of the local group sit other small kingdoms, each its own little family of galaxies. The Sculptor group, strung out below us. The Maffei and IC 342 group, half hidden behind the dust of our own galaxy. The M81 group, farther out, with its own giant tearing at its own captives. Little local groups, over and over, scattered through the nearby dark, each one a household of galaxies keeping to itself. And when you pull back far enough to see how all of these households are arranged, a shape appears that no one would have guessed. They are not scattered randomly through space in every direction. We and our neighbors all lie pressed into a thin, flat layer, a broad sheet of galaxies spread out like objects resting on a tabletop, wide across and remarkably shallow. Astronomers call it the local sheet, and our entire local group is just one small knot within it. So the question sharpens on its own. Why flat? Why would galaxies settle into a thin layer instead of filling space evenly in all directions? And the answer lies in what sits directly above that sheet. Nothing. An immense, near-perfect emptiness called the local void, stretching some 65 million light-years across, holding almost no galaxies at all. It presses down against our sheet from one side, and our sheet forms part of the wall that contains it. We live, in other words, at the edge of a vast hollow. On one side, the crowded thread of the local sheet, full of galaxies and groups and hermits. On the other, An emptiness so large and so barren that only a handful of lonely galaxies have ever been found drifting inside it. And that emptiness is not passive. Something about all that. Nothing is shaping the sheet, flattening it, and quietly shoving our whole neighborhood away from it, which should stop us cold. Emptiness is not supposed to do anything. A void has no matter, no mass, no gravity of its own to speak of. It is, by definition, the absence of things. So how can a region of pure nothing reach across millions of light years and push an entire sheet of galaxies, including this cluster, including you, as if the nothing itself had a hand to shove with? Nothing has no hand. Emptiness cannot reach across space and shove you. And yet, we really are being driven away from a vast, empty region at enormous speed right now. The resolution to that contradiction is one of the cleanest ideas in all of cosmology, and it needs no new physics whatsoever. The emptiness does not push. It simply stops pulling, and everything else wins. Picture yourself floating in the middle of a great crowd, and every person in it is holding a rope tied to you, pulling gently toward themselves. Surrounded on all sides, all those pulls cancel, and you hang there perfectly still, going nowhere. Now let one whole side of the crowd drop their ropes and walk away, leaving an open gap. No one has pushed you. Not a single hand touched you. But the people on the far side are still pulling, and with nothing opposing them now, you begin to drift, slowly, steadily, away from the empty gap and toward the crowd that never let go. That is precisely what a cosmic void does to us. In a universe spread out perfectly evenly, gravity would tug on our galaxy from every direction at once, and it would all cancel, and we would sit still against the background. But the universe is not even. In one direction from us lies a huge region where the matter is missing, a void, and so the pull from that side is feeble. In the opposite direction lies ordinary matter, galaxies and clusters pulling with full strength. The two no longer balance, and we slide away from the emptiness. So when astronomers say a void repels us, they mean something exact and unmysterious. Measured against the average density of the universe, a place with too little matter behaves, in the arithmetic, just like something pushing us away would. But there is no anti-gravity out there, no strange new force, no negative mass. There is only ordinary gravity, always pulling, always attractive, and a hole in the matter on one side that lets the other side win. The push is a shortfall, wearing the costume of a shove. And we can measure exactly how hard that shortfall works on us. The nearest of these emptinesses, the local void sitting right at our doorstep, drives us outward at about 260 kilometers every second, roughly 160 miles a second. Set that against our total motion through the universe, the 630 kilometers a second we clocked against the ancient light. Nearly half of our entire journey through the cosmos is not a fall toward anything at all. It is a drift away from a place where nothing is. And the local void is only the near part of the story. In 2017, astronomers mapped the flow of thousands of galaxies through our region of space, tracing not just where things are, but which way everything is moving. And far off in the direction we are fleeing from, some 700 million light-years away, they found an enormous underdensity, a supervoid so vast and so empty that it had gone completely unnoticed because there was almost nothing there to see. They named it the dipole repeller. It solved a puzzle that had nagged for decades. The dense Shapley concentration, off on the far side, had long been the suspected cause of our speed, but on its own it could only explain about half of it. The rest was the repeller. A giant emptiness behind us, pushing by not pulling, and a giant crowd of galaxies ahead of us, pulling directly. Void at our back, density at our face, both driving us the same way down a single line. Together, they account for how fast we truly move. Once you see the map that way, something quietly turns over in how you picture the whole universe. We have spent this entire night following the matter. Galaxies, halos, streams, dwarfs, the bright and the dark things that fill our home. But the honest map of the cosmos is mostly the other thing. The galaxies and clusters are strung along thin threads and gathered into small knots, and between those threads lie the voids, enormous and dark, taking up the overwhelming majority of all the volume there is. Emptiness is not the exception out there. Emptiness is the rule. The somethings, the galaxies and stars and worlds, are the rare crowding, the thin, bright filigree threaded through a cosmos that is, by volume, almost entirely nothing. And that nothing is not a passive backdrop. It shapes the sheets we live in. It flattens them. It steers our motion as firmly as any cluster does. The absence is a full partner in the architecture. There is a strange comfort in that, at least for me. We are a rare little knot of presence, held in place and gently shoved along by the vast, quiet emptiness that makes up most of what exists. The void is not hostile. It is simply the larger share of things, the ocean that our small islands of matter float within. To belong to the universe is mostly to belong to its spaces. But even here, we've been leaning on a comfortable assumption, and the next step pulls it out from under us. All night we've talked about weighing our home, about trillions of suns of mass, about giants and halos and the pull that holds everything together. We've been treating that matter as the solid, countable, knowable part of the story. The part we can see. And when we finally sit down and weigh the local group with real honesty, adding up everything we can actually point to, we find that nearly all of it is missing. Almost nothing in our home is anything we have ever seen. To weigh a house you cannot step outside of, and cannot place on any scale, you need a different kind of cleverness. And in 1959, two astronomers found it almost by accident. Franz Kahn and Lodewijk Volcher were not hunting for missing mass at all. They were trying to explain a gentle warp in the outer gas of the Milky Way. And in passing, with 3 numbers and a single idea, they weighed the entire local group and stumbled straight into one of the deepest problems in physics. Their idea was beautifully simple. Long ago, just after the Big Bang, the Milky Way and Andromeda must have been packed together in nearly the same spot. The expansion of the universe then carried them apart, farther and farther, for billions of years. And yet, look at Andromeda now, and it is not receding. It is coming back, falling toward us at a bit over 100 kilometers every second. Something reached out across all that distance, halted their separation, and reeled them back in. That something is gravity, and the amount of it decides how heavy the 2 galaxies must be. So they set up the problem like a swing. Take the age of the universe, the time available for the whole out and back journey. Take the current distance between the 2 galaxies. Take the speed at which Andromeda is now approaching. With just those 3 measurements, you can solve for the mass it would take to have turned that vast expansion around and pulled the 2 giants back toward each other in the time allowed. The answer that fell out was staggering, and it has held up for over 60 years. The local group weighs somewhere between 3 and 5 trillion times the mass of the Sun. And here is the part that broke everything open. That total is at least 20 times heavier than all the visible stars in the local group combined. Let me make that ratio something you can hold. Imagine every star that shines in our home, in both giant galaxies and all 100 dwarfs, added up into a single dollar. The true mass of the local group, the weight gravity actually demands, would be something like $6 to $10. And of those extra dollars, almost none are in any form that a telescope has ever seen. The light we have followed all night, every star in the story, is barely the loose change. So where is the rest? The answer comes in two parts, and only one of them is comforting. Kahn and Wolter's own first guess was ordinary matter we simply can't see easily. Thin, hot gas, filling the space between the galaxies, too diffuse and too faint to glow noticeably. And they were partly right. There is such gas at millions of degrees, and it holds a real share of the missing weight, the so-called missing baryons that took us decades to begin locating. But when you add up every scrap of gas we can account for, it still falls far, far short. The rest, the great bulk of it, is dark matter. Not gas, not dust, not faint stars, not anything made of the ordinary particles that make up you and this planet and every atom you have ever touched. Something else. Something that has mass and pulls with gravity and does nothing else we can detect. Of everything holding the local group together, only about 1/6 is ordinary matter of any kind, and only a sliver of that 1/6 shines. The other 5/6 is a substance no one on Earth has ever identified. We have drawn a careful, loving map of our home, named its members, traced its edges, followed its fall. And when we finally weigh it, we find that we can see and name only a few % of what it actually is. The house is overwhelmingly built of something we cannot look at, cannot catch, and cannot yet explain. What if the measurement is wrong, and there is no invisible substance at all? It is the right thing to ask, and people have asked it seriously. Maybe we are miscounting the gas, though the gap is far too wide for gas alone to close. Or maybe, more radically, our theory of gravity itself is slightly off on these enormous scales, so that ordinary matter pulls harder than our equations say, and no dark matter is needed. That idea has a name, modified gravity, and a small number of thoughtful researchers pursue it. I want to give that view its fair hearing, because honesty demands it. But it is only fair to add that this same local group is one of the places modified gravity struggles most. Applied here, it tends to predict even less mass than the visible matter alone, and it can only fit the galaxy's motions by asking them to move along strange, contrived paths. So the descent is real, and it is taken seriously, and it does not cleanly rescue us either, which is why most of the field, following the weight of the evidence, accepts the harder answer. The missing mass is really out there, and we do not know what it is. There is a vertigo in that, if you let it come. To live your entire life inside a structure and learn that nearly all of it is something you could never see or hold. But sit a moment longer with the shape of it, and the fear softens into something else. That invisible majority is not lurking, not hostile, not waiting. It is the scaffolding. It is the very thing whose gravity gathered the gas, lit the first stars, held the galaxies together long enough for planets and oceans and you to happen at all. The dark is not the enemy of the light. It is the frame that lets the light exist. We wait a home we cannot name and found that most of it has been quietly holding us the whole time. But this invisible scaffolding is not shapeless. It has structure, and that structure leaves fingerprints in how the small galaxies move around the big ones. And when we finally look closely at those motions, expecting the tidy swarm that invisible mass is supposed to produce, we find something else entirely. The satellites are lined up. Arranged in a thin spinning sheet they have no business forming, as if something told 100 scattered galaxies to fall into a single row. Our best theory of how the universe builds itself makes a clear prediction about the small galaxies orbiting a giant like ours. They should arrive from every direction, falling inward along the invisible threads of the cosmic web, and settle into a loose, roughly round swarm around their host. A cloud of dwarfs, scattered on all sides, orbiting every which way. That is what dark matter and the whole standard model of cosmology tells us to expect. That is not what we see. What we see is 100 small galaxies that appear to have been told to fall into a single row. The first hint came back in 1976 when the astronomer Donald Lynden Bell noticed something odd about the Milky Way's known companions. They did not surround us evenly. They lay strung along one great circle across the sky, the same circle traced by the long stream of gas trailing from the Magellanic Clouds, a ring standing nearly straight up from the flat disk of our galaxy. For years, that could be brushed off as a small sample accident. But as we found more satellites, the pattern held. And when we finally measured how they move, the accident got much harder to dismiss. They are not just arranged in a plane. They are orbiting within it, together, like a thin spinning disk of dwarf galaxies wrapped around our own. Astronomers named it the vast polar structure, and for a while you could still hope it was ours alone, a quirk of the Milky Way. Then, in 2013, Rodrigo Ibata's team turned the same careful eye on Andromeda. And there it was again. About half of Andromeda's satellites, 15 of them, lie in a single thin plane, over 1 million light-years across, but only tens of thousands thick, far flatter than a dinner plate. And because we see that plane edge on, the motion gives itself away cleanly. The satellites on one side are all moving toward us, and the ones on the other side are all moving away. The whole sheet is turning. Two great galaxies, side by side in the local group, each ringed by a thin spinning disk of dwarfs. And then a third, the galaxy Centaurus A, farther out, showed the same arrangement. 3 for 3. Whatever this is, it is not a fluke of one crowded sky. And that is a real problem, because it collides with the very model we leaned on a moment ago to weigh our home. When cosmologists build universes inside their computers, seeding them with dark matter and letting galaxies assemble, satellites almost never fall into thin, co-rotating disks like these. Run the simulations, and arrangements this flat and this organized show up in only a few % of cases, sometimes fewer. To find one would be surprising. To find 3, next door to each other, starts to feel like the theory is missing something. So we are left with a genuinely open puzzle, and several ways to read it. One possibility is that these dwarfs are not ancient, independent galaxies at all. They might be debris. When two large galaxies collide and tear at each other, the wreckage flung out into space can gather into small new galaxies of its own, born together, moving together, naturally strung along a single plane like sparks off a struck wheel. That would explain the neat rotating sheet immediately. But it clashes with something we already measured. Galaxies made from collision debris should carry almost no dark matter, and yet these satellites, the faint ghosts from earlier tonight, are among the most dark matter-dominated objects we know. The debris idea explains the shape and breaks the weight. Another possibility is gentler on the standard model. Perhaps the satellites really did fall in from the cosmic web, but not from every direction equally. The threads of that web are not random. Near us, they may funnel infalling dwarfs along preferred directions, and the great emptiness of the local void, pushing from one side, may help flatten their arrangement into something disk-like. In that reading, the plane is not a crisis at all, just a subtler consequence of how matter flows around the voids we met earlier. And there is a third, more deflating possibility. Maybe the planes are not permanent. Maybe they are fleeting arrangements, disks that form and dissolve over time, and we simply happen to be watching during the brief window when the satellites line up. Some recent work argues exactly this, that the significance was overstated, that the tidy plane is partly in the eye of the observer, and that the tension with the standard model may be smaller than it first appeared. I have to be honest with you about where this stands. We do not know which of these is right. Some astronomers call the planes of satellites one of the sharpest cracks in our theory of the universe. Others believe the crack has already been sealed. The argument is live and unresolved, and being fought over in the literature right now. What stays with me is a quieter thing about how we react to it. Chaos we can live with. A messy, scattered swarm of dwarfs would have troubled no one. It is the order that unsettles us. A sky arranged into a clean, spinning ring feels like it is trying to tell us something, like a sentence written in a language we haven't learned. And the hard discipline, the honest work, is to keep asking whether that order truly carries a message about how the universe is built, or whether we are pattern-hunting animals reading meaning into a chance arrangement of lights. We do not yet know which it is. But the answer matters more than it seems, because it decides something about time. If these dwarfs are ancient, they are among the oldest witnesses in the local group, and their arrangement is a message from the deep past. If they are debris, they are young, and the message is about a more recent catastrophe. Either way, the question turns on whether our companions are old settlers or recent arrivals. And one of those companions hangs low in the southern sky tonight, close enough to see with your own eyes, holding a secret that overturns everything we assumed about how long it has been here. Look south tonight, if the sky over you allows it, and you will find two soft patches of light drifting near the horizon, like torn pieces of the Milky Way set loose. The large and small Magellanic Clouds. They have hung in the southern sky for the whole of human history, storied and steered by for tens of thousands of years, long before a European voyage lent them the name we use now. For every person who has ever looked up from below the equator, they have simply always been there. And for 50 years, astronomers agreed with that feeling. The clouds were old companions, family, small satellites that had circled the Milky Way over and over across billions of years, bound to us since the beginning. It was in the textbooks. It felt settled. And then someone measured how they actually move, and the certainty came apart in her hands. In 2006 and 2007, Nitya Kalavealil pointed the Hubble telescope at the clouds and made the same brutal measurement we met before, the sideways drift, the proper motion that is so hard to catch. She tracked them against distant background objects across 2 years, and the number that came back was not what anyone expected. The clouds were moving nearly 100 kilometers a second faster than the old models allowed. The large cloud alone was racing along at around 350 kilometers a second, roughly 220 miles every second. And that speed carries a hard consequence. It is right at the edge of the Milky Way's escape velocity, the speed above which something is not orbiting you at all, but flying past. Family does not move at escape velocity. A body that has circled you gently for billions of years does not come tearing through at the exact speed of something on its way out the door. That single measurement broke the picture of the clouds as ancient companions and replaced it with something stranger. The new reading is that the Magellanic Clouds are newcomers. They are most likely falling toward us for the very first time, arriving from the far outskirts of the local group, or at best swinging on an orbit so enormous it takes many billions of years to complete. Either way, they have not been looping us since the dawn of time. They are recent arrivals, caught in the act of coming in. And other clues line up behind it. The large cloud is still full of gas, still busily forming new stars, still bright and messy and alive, when a satellite that had orbited us for billions of years should long ago have had its gas stripped away and its star-making stilled. It does not look like something we have been slowly wearing down. It looks like something that just got here. This rewrites another thing we thought we understood, a long river of gas called the Magellanic Stream. It trails behind the clouds across 150 degrees of sky, an enormous ribbon of hydrogen, and it is young, only 1 billion or 2 years old. For a long time we assumed the Milky Way's gravity had torn it out of the clouds as they orbited. But if the clouds only just arrived, our galaxy never had the time to do that. So the gas was pulled loose another way. The two clouds, falling in together as a bound pair, have been tearing at each other, one wrenching gas from the other, a small violence between the two of them that has nothing to do with us at all. And now the story turns, the way it did with Sagittarius, and looks toward what comes next. The large cloud is not a trivial thing. Its mass is a real fraction of our own galaxies, and it has just swept through its closest approach, a mere 160,000 light-years out. Its orbit is decaying, and the models point to a clear ending. In roughly 2 billion years, the large Magellanic Cloud is expected to spiral in and merge with the Milky Way long before Andromeda ever arrives, if Andromeda arrives at all. We met the predator in ourselves a while ago, unwinding Sagittarius across the sky. The clouds are the next meal. The difference is that this one you can see with your own eyes, hanging there tonight, bright and gas-rich and doomed, a galaxy we will consume before our own collision with Andromeda is even decided. And its arrival may not go quietly. When a mass that large falls into the center of a galaxy, it does not simply vanish. It drags gas inward, down toward the great black hole sleeping at the Milky Way's core, the one we call Sagittarius A star, which right now sits quiet and nearly starved. The models suggest the cloud's arrival could feed it, funneling fresh fuel into its reach, waking it, swelling it, perhaps igniting it briefly into a blazing beacon at the heart of our galaxy. The newcomer we can see tonight may be the thing that finally lights the fire at the center. There is something about all of this that stays with me after the numbers fade. For every human who has ever lived, the Magellanic Clouds were permanent. Fixed points. Eternal lights to navigate by and tell stories about. And that permanence was always an illusion of scale. Always, for a person, is a handful of decades. Always, for a galaxy, is billions of years. And on that clock, the clouds are brief visitors, here for a moment, on their way to being absorbed. The most familiar thing in the southern sky is one of the most temporary. And that reframes the whole neighborhood one more time. If the clouds only just arrived, and Sagittarius is being eaten as we speak, and an entire galaxy was swallowed 10 billion years ago, then the local group is not a finished place. It is not a settled arrangement of ancient members holding their positions. It is a construction site, still taking deliveries, still assembling itself, right now. Which forces the oldest question there is about any home. Out of what was it built, and when did the building begin? We cannot watch the building happen. The construction of our home finished its major work billions of years before anyone was here to see it. But the builders left evidence behind, scattered through the stars, and slowly we have learned to read it. Every old star around us is carrying a record of where it came from, if you know how to look. There are 2 fossils buried in a star, and each tells a different part of the story. The first is its chemistry. The universe began with almost nothing but hydrogen and helium, and every heavier element, the carbon, the iron, the calcium, was forged later inside generations of stars that lived and died and seeded the next batch. So, a star that is poor in heavy elements was born early, or born in a small galaxy that never built up much enrichment. Its chemical makeup is a birth certificate, stamped with roughly when and where it formed. The second fossil is how it moves. The stars born inside the Milky Way's disk all share the disk's spin, circling the center in the same broad direction, like a great flock turning together. But a star that orbits some other way, tilted, or plunging in and out, or turning against the flow, could not have been born here. It came from somewhere else, fell in, and was absorbed, keeping the motion of its lost home. The way a star moves is a fingerprint of its origin. For most of history, we could not read these fossils because we could not measure the motions precisely enough. Then came Gaia, a telescope built to do one thing with almost unbelievable care: to map the positions and movements of nearly 2 billion stars. And once we could sort the sky not by how stars look, but by how they move, the buried history rose to the surface. The first great discovery surrounds you right now. About 30,000 stars spread all around our part of the galaxy that move the wrong way. Not around, with the disk, but in and out, on long radial plunges through the galaxy, like divers instead of dancers. They did not form in the Milky Way. They are the remains of an entire galaxy that fell into ours and was torn apart roughly 10 billion years ago. We call it Gaia Enceladus, or the sausage, that second name coming from the odd sausage-like shape those stars trace out when you plot their speeds. It was the last truly major collision our galaxy ever suffered, and it built much of the halo around us and thickened our disk in the process. And Gaia Enceladus was not alone. Once we knew how to find one swallowed galaxy, a whole family tree unfolded. There is Sequoia, a population of stars orbiting firmly backward against the spin of everything else, the ghost of another devoured galaxy. There are fainter traces, several of them. And there is one that may be the oldest and largest of all, a galaxy we call Kraken, that merged with our infant Milky Way some 11 billion years ago, when ours was still small and the collision loomed all the larger for it. Piece it together, and our galaxy is built from the wreckage of at least 5 separate galaxies, most of them gone before the sun was ever born. Once you know that, the night sky changes character. The stars around you are not all natives of this place. Many of them are refugees, survivors of galaxies that no longer exist, still wheeling through our halo on the paths of their vanished homes, still carrying the plain chemistry of worlds that were swallowed before Earth had formed. We live in the calm aftermath of ancient collisions, and we are only now learning to read the names of the dead in the motions of the living. That reading also lets us compare ourselves to our twin. Our own record, after that one great merger, is surprisingly gentle. For 10 billion years, the Milky Way has mostly grown quietly, from the slow cooling of its own gas rather than from repeated violence. Andromeda's fossils tell a rougher story. Threaded through its halo is an enormous ribbon of stars we call the giant stellar stream, the debris of a substantial and more recent collision. The scarred sibling and the quiet one, from earlier tonight, turn out to have the injuries and the calm written right into their oldest stars. And this points at something deeper about how we can know any of it. When our largest telescopes stare far across the universe, they are looking back in time, seeing galaxies as they were billions of years ago. But that view is a photograph. A single frozen instant of a distant stranger whose later life we will never witness because the light showing us its youth is the only light we will ever get from it. Our own local group lets us do the opposite. Here, and only here, we can dig. We can excavate the buried past of a single galaxy, star by star, and reconstruct its entire life story from the fossils it left in its survivors. The far universe gives us photographs of others. Our home gives us the one complete biography we will ever be able to write. There is a strange intimacy in that work, and it stays with me. We are doing forensics on our own birth. Standing at a crime scene 10 billion years cold, reading the evidence off the paths of the few stars that live to tell it, writing eulogies for galaxies whose only remaining names are the ones we invented for their ghosts. The place we belong to is a graveyard and a family tree at the same time, and we are its first archaeologists. The fossils all point the same way. Our home was assembled, slowly, out of smaller things, over billions of years, and the assembling is not even finished. Run that film backward far enough, and you reach a beginning, a scattering of small pieces in the young universe. But run it forward, past tonight, past the arrival of the clouds and the long fall toward Andromeda, and the film does not simply stop. It reaches an ending. One house, one light, and then a very long night. So the question we have been circling since the very first minute finally has to be asked in full. What does our home become when all the building is done? When all the building is finished, our home becomes a single galaxy, alone, in a sky with nothing else in it. Move forward about 100 billion years, roughly 7 times the entire age the universe has reached so far. By then, the bound members of the local group have done what gravity always meant them to do. Whether or not the Milky Way and Andromeda collide in the next 10 billion years, on this far longer clock they, and the dwarfs, and everything else still tied to us, fall together and merge into one vast elliptical galaxy. A single smooth island of stars, our whole crowded neighborhood fused into one. And around that island the sky has gone dark. Not dimmed, emptied. Every other galaxy is gone. The reason is the accelerating expansion we keep running into, the push of dark energy. The farther a galaxy sits from us, the faster the growing space between carries it away, and past a certain distance, the cosmic horizon, that retreat becomes effectively faster than light can cross. Light, leaving those galaxies now, will never reach us. And as the expansion keeps speeding up, that horizon draws steadily inward, and one by one, the galaxies beyond it slip across, redshift toward invisibility, and wink out for good. Today, we can see more than 400 billion galaxies. In 100 billion years, every last one of them beyond our own merged home will have crossed that line and vanished. A sky that holds hundreds of billions of galaxies tonight will hold exactly one. A single lit house, standing in an ocean of dark that gives back nothing. And the loss goes deeper than the galaxies. The ancient light we leaned on earlier, the faint afterglow of the beginning that we used as our speedometer against the universe, will suffer the same fate. Its waves, stretched further and further by the expansion, will grow so long and so faint that no instrument could catch them, until the clearest surviving fingerprint of the Big Bang is simply gone from the sky. The mirror that showed us our own motion will have dissolved. This is the part that unsettles me most, and it lands quietly. The three great pieces of evidence that told us the truth about the universe all disappear together. The galaxies fleeing from one another, gone, because there are no visible galaxies left to flee. The afterglow of the beginning, gone, stretched past detection. The record of the first elements, read from distant light, gone with the distant light itself. Every pillar that holds up the story of where everything came from will have been removed, not by carelessness, but by time. So picture the astronomers of that era, living in the merged galaxy, doing careful and honest science. They point their instruments outward and see one static island of stars surrounded by perfect blackness. No motion. No other galaxies. No afterglow. And from that honest evidence, they reach a reasonable, careful, and completely wrong conclusion: that they live in a single, eternal, unchanging universe, and always have. The ache of it is that this is exactly the mistake we ourselves made just over a century ago. In 1908, before Hubble, our best scientists believed our galaxy was the entire cosmos, a lone island of stars in an infinite still void. We climbed out of that era for one reason only. The evidence was still there to be seen. The future minds in Milky will fall back into the very same picture, and this time there will be no climbing out, because the universe will have quietly erased the story of its own origin. And that reveals something I find genuinely sobering about knowledge itself. The truth about the universe is not permanently available. There is a deadline on it. Facts we hold as settled, the expansion, the beginning, the dark energy driving it all, are readable only during a certain window of cosmic time, and outside that window they become, for any observer, undiscoverable. We happen to be alive inside that window. We are among the last who will ever be able to look out and see the whole story written plainly across the sky. Readers in a lit library, in the brief age before the books are checked out, one by one, and never returned. I want to leave you with the other side of this, though, because it is just as true, and it is gentler. The same physics that isolates Milkomeda also protects it. Our local group is gravitationally bound, and that binding is permanent. While the rest of the universe recedes into cold and dark, our merged home holds together, warm and lit and stable, for the rest of time. The isolation is also a shelter. The dark grows out there, far away and slow, and inside it our single house keeps its lights on, unbroken, for longer than the mind can hold. So the shrinking of the sky is not only a loss, it is also the drawing in of a home that will never come apart. And you are here now, in the one era when the whole of it can still be read, holding the entire story in your mind tonight, from the first light to the last galaxy. That is not a small thing to be given. But even standing here, in this bright and privileged window, with the evidence still spread out around us, we have not answered everything. Far from it. For all that we can see tonight, that future minds never will, our own home still holds questions we cannot yet crack, sitting right here inside the sheltered dark, close enough to touch, and still refusing to give up their answers. And some of them go to the very foundation of everything we have said we know. Our home is the single best-studied structure in the entire universe. And it is still full of open cases. For all we have traced tonight, there are questions sitting right here inside our own neighborhood that we cannot yet answer, and one of them is almost embarrassing in how basic it is. We do not know how much our own galaxy weighs. Not even close, really. The best measurements of the Milky Way's total mass still span a factor of 2, from roughly one figure to double that figure, with the truth somewhere in between. Put that in human terms. Step on a bathroom scale and have it tell you that you weigh somewhere between 140 pounds and 280. Take your pick. That is the precision we have on the weight of the galaxy we live inside. And that single fuzzy number is the keystone holding up half the puzzles in this story. The odds of ever colliding with Andromeda depend on it. Whether the Magellanic Clouds are first-time visitors or old companions depends on it. Even the location of the invisible edge of home, the balance shell we drew, depends on how much we weigh. One unknown number, quietly holding several of the night's biggest answers hostage. Then there is the problem of the satellites, and it has 2 faces. The first we met early on. The theory predicted our galaxy should have hundreds or thousands of small companions, and for a long time we saw only dozens, though the ultra-faint ghosts have slowly been filling that gap. But the second face is sharper, and it has not gone away. The same theory predicts that a handful of our dark matter clumps should be truly massive and dense, so large that they were, in a sense, too big to fail at forming a bright galaxy. They should have lit up. And yet the brightest dwarfs we actually see are not dense enough to be those giants. So either there are massive, heavy halos out there, real and starless and still undiscovered, or the dark matter itself does not behave the way our models insist. Neither answer leaves the foundations untouched. There is a gentler mystery, too, about how these small galaxies die. Remember the isolated hermits, the ones like Cetus and Tucana, quiet and starless far out on their own, though nothing ever came close enough to strip them. We still cannot fully say what silenced them. And more broadly, our models keep disagreeing with the sky about which dwarfs should have gone dark and which should still be forming stars. Something switches these little galaxies off, and we have not pinned down exactly what or when. And hanging over all of it is the lined-up sky from before, the thin spinning plane of satellites that our best theory says should not exist, and that we still cannot agree is a real crisis or a trick of timing. Now, it would be easy to hear all of that as a list of failures. It is closer to the opposite. These are not separate, scattered gaps. They interlock. Several of them tighten or loosen together the moment we finally nail down that one keystone number, the mass of the Milky Way. What looks like a pile of unrelated mysteries is really a single tangled knot, and we can see the strand to pull. And there is a discipline underneath this that I have come to admire. All night, without always naming it, we have been sorting every claim into 3 honest bins. The things we have directly measured, like the positions of galaxies and the shift of their light. The things we infer through a model, like the invisible mass we deduce from how stars move. And the things still contested, still argued over in the journals right now. A science mature enough to keep that ledger in public, to say plainly, this we know, this we deduce, this we do not yet agree on, is a science you can trust precisely because it refuses to pretend. And this is where our moment differs from that far future we imagined. The astronomers of Milky Way will lose their evidence. We are gaining ours. In June of 2025, a new observatory named for Vera Rubin opened its eyes for the first time, and in its very first images, still just testing its camera, it already turned up a long, shredded stream of stars trailing from a distant galaxy. Its full survey will sweep the sky again and again, hunting exactly the faint dwarfs we are missing, mapping the star streams that will finally weigh our galaxy, and testing whether that lined-up plane is real. Another great telescope, Roman, follows close behind. And our star maps grow sharper every year, tightening the odds on the collision itself. So the jurors are still filing into the room. The evidence tables are filling, not emptying. The verdict is not in on the mass, or the missing giants, or the dying dwarfs, or the plane. But unlike the minds of the far future, we live in the window when these cases can still be tried, and many of them may be settled within a single human lifetime, perhaps within yours. There is a quiet comfort in that I did not expect. Open questions are not a sign that something has gone wrong. They are the sign of a living inquiry, caught in the rare and lucky moment when the answers are still reachable. To lie here tonight, knowing the questions and knowing the instruments to answer them are already switching on, is a kind of privilege the future will not have. We get to wonder while wondering still works. And notice what this unfinished, argued over, half-measured home managed to do, despite refusing to answer so much. Somewhere in this quiet pocket of gravity, out of swallowed galaxies and patient chemistry and billions of undisturbed years, it built something no simulation was asked to predict. It built a mind. A small, warm, curious mind, capable of lying in the dark and asking how big its home truly is. And that may be the strangest achievement in the whole story, stranger than the dark matter or the empty edge or the long fall. So the last question left to ask is, why here? Why this particular neighborhood, out of all of them, was calm enough to grow someone able to notice it at all? The thing that kept stopping us was scale. The vastness, the trillions of suns, the millions of light years, the sheer enormity of home. But the feature of this place that may matter most for why we are here at all is not its grandeur. It is how quiet it is. To feel the difference, imagine we had grown up somewhere else. Not in a small, loose group of a few dozen galaxies, but in a rich cluster, a place like Virgo, where more than 1,000 galaxies are packed together and swarming. A galaxy living there does not drift through gentle emptiness. It plows through a hot, dense sea of gas that fills the whole cluster, moving at more than 1,000 kilometers a second, over 2 million miles an hour. And at that speed, that sea acts like a wind. We have a name for what that wind does. Ram pressure stripping. The cluster's gas tears the galaxy's own gas right out of it, peeling away the raw material for new stars and leaving the galaxy starved, unable to make more. On top of that comes constant harassment, near misses with other galaxies again and again, each one battering and reshaping and stirring. Galaxies in clusters end up gas-poor, reddened, their spirals smoothed into lifeless shapes. Had the Milky Way formed in a place like Virgo, it might well have been stripped bare and beaten out of shape long before anything here had a chance to begin. Our group gave us the opposite. A few dozen galaxies instead of 1,000, spread through cool, thin space instead of a searing, dense medium. No punishing wind. No endless battering. The great spirals kept their gas, kept quietly forming stars across billions of years, and kept their thin, orderly disks and their calm, settled orbits. A sheltered harbor rather than a violent current. And that calm runs deeper than just the neighborhood. It is written into our galaxy's own history. The Milky Way has not suffered a truly major collision in about 10 billion years, and that long piece kept its disk thin and its orbits close to circular. A galaxy hammered by repeated mergers would have a puffed-up, churned, chaotic disk, its stars flung onto disordered paths, its gas repeatedly slammed into violent bursts of new stars and the supernovae that follow. Ours stayed smooth. The sun's own steady, nearly circular journey around the galaxy, held for billions of undisturbed years, may owe a real debt to that piece. Because the violence is not only a matter of shape, it can be lethal. A supernova or a gamma-ray burst going off too close can wash a planet in radiation fierce enough to sterilize it, and those catastrophes cluster in the dense, fast-burning, metal-poor regions of a galaxy. A quieter neighborhood means fewer of those blasts nearby across the long stretch of time that life needs to slowly find its footing. The calm did not just let a disk stay tidy. It may have kept the lights from being switched off before anyone could arrive. There is an idea called the galactic habitable zone, a proposed Goldilocks region of a galaxy with enough heavy elements to build rocky worlds, yet far enough from the deadly inner regions to stay safe. It is a reasonable idea and a useful one, but it is a hypothesis, not a settled law. Its boundaries shift depending on whose model you use, and it is argued over. And we are reasoning, in the end, from exactly one inhabited planet. So the story that our calm surroundings made us possible is plausible and grounded in real mechanisms we can measure, but it remains a story told from a sample of one. Still, hold the shape of it, because it quietly inverts something we almost always assume. We tend to think life must need somewhere special. Somewhere grand, or central, or spectacular. And the evidence, as far as it goes, points the other way. Life may need somewhere calm, somewhere overlooked. Not the roaring heart of a great cluster, but the quiet outskirts. Not the violent, dramatic galaxy, but the gentle one that was mostly left alone. We may be children of the stillness, not the grandeur. And that carries a hopeful thought out into the wider universe. Rich, violent clusters are actually the exception. Most galaxies, across all of space, live in small, quiet groups much like ours. Gentle harbors are not rare. They may be the ordinary condition of things. Whether the full recipe that made us, the quiet group, the peaceful history, the right chemistry, the steady orbit, is common or vanishingly rare, we honestly do not know. But the calm itself, the single ingredient we can most clearly point to, is spread generously through the cosmos. Whatever we are, the conditions that may have allowed us are not unique to this one address. After all the vastness, all the trillions and the millions of light years, the thing that may have made us was smallness. Quiet, being passed over by the violence. The least dramatic feature of the least dramatic corner of the sky may be the one that matters most to the fact that anyone is here to look. And that changes what this whole map has been. Every chapter tonight, we thought we were charting geography, the shape and size and edges of a place out there. But if this quiet pocket of gravity is what grew us, then the map was never only about the sky. It was about us. Every heavy atom in your body, the iron, the calcium, the oxygen, was forged and gathered and assembled inside this one gentle gravitational pocket over billions of years and never left it. So the map we have been drawing all night is not a picture of somewhere you live. It is a picture of what you are made of. Take that literally, because it is literal. The hydrogen in the water that fills you came out of the Big Bang itself, almost 14 billion years ago, older than any star. The carbon in every cell, the oxygen in every breath, were cooked inside stars that lived and died before the sun existed. And the calcium holding your bones together, the iron riding in your blood right now, carrying oxygen to your brain as you lie here, were forged in supernovae. In the explosive final moments of massive stars, blowing themselves apart and seeding space with the very atoms you are made of. You are not a witness to this neighborhood. You are a piece of it. Every heavy atom in your body was manufactured somewhere inside this gravitational pocket, over billions of years, and then gathered, about 4.5 billion years ago, into the slowly collapsing cloud of gas and dust that became the sun, the earth, and eventually you. You were assembled here, slowly, patiently, out of the ashes of local stars. And some of those ashes may not even be native. Remember that our galaxy grew by swallowing others, and that the gas which built the sun had been enriched by generations of stars, some of them belonging to galaxies the Milky Way devoured long before the sun was born. Galaxies like the one we swallowed 10 billion years ago, whose only remaining name is the one we invented for its ghost. Which means it is entirely possible that a fraction of the atoms in your hand tonight were forged inside a galaxy that no longer exists. That you are carrying, in your bones and your blood, the scattered remains of vanished worlds, folded so completely into you that nothing but their history remains. And you are not still. Lying here in the dark, perfectly at rest, you are being carried by a whole stack of motions at once. The earth turns beneath you. The earth carries you around the sun at about 30 kilometers a second, faster than any rocket we have ever built, while you do nothing but breathe. The sun carries you around the galaxy at more than 200 kilometers a second, on a loop so vast that a single trip takes about 230 million years. The last time the sun sat exactly where it is now on that great orbit, the first dinosaurs were only just appearing on Earth. You have never once completed a full lap. No human ever will. And beneath all of that, the entire local group is carrying the whole arrangement, sun and galaxy and you, at more than 600 kilometers a second, toward that hidden mass we can never quite see. You are moving in at least 4 different directions at the same time, wrapped in motion, inside motion, inside motion. And you feel none of it, because all of it moves with you, and everything that falls together feels perfectly, completely still. There is one more thing about your place here, and it is the deepest of all. You cannot leave. Not the Earth, not the Sun, not any craft we could ever build. You are bound to the local group by gravity, and that binding holds for the rest of time. You have been inside this structure for every single second of your existence, and you always will be. When the sky finally empties, when every other galaxy has slipped beyond the edge of what can be seen, you, or whatever you have become, will still be here. This is the one address in the universe that is truly, permanently yours. And I know how that could sound. Like a sentence. A structure you can never escape, holding you for eternity, whether you like it or not. But turn it over, gently, and it becomes the opposite. The same gravity that will never release you is the gravity that keeps you from being scattered. Out beyond the edge, everything is being pulled apart, thinned into the cold and the dark, carried off forever. In here, you are held. It is not a cage. It is a keel, the deep, steadying weight down in the hull that keeps a ship from capsizing, that keeps it from being lost. The bond you cannot break is the bond that will not let you be broken. Belonging you cannot escape is also belonging you can never lose. I have spent this whole night describing a place out there far away, enormous and strange. And the quiet truth underneath all of it is that there is no out there. You are not looking at the local group. You are inside it, made of it, moved by it, and held by it at this very moment, in the dark, under whatever roof you are lying beneath. The map we drew all night was never of somewhere else. It was a mirror. So all of it comes down to this. All the vastness we crossed, the 80 and more galaxies, the invisible mass, the empty pushing voids, the long unfelt fall, the edge made of nothing, the sky that will one day close. All of that immense machinery, and the night still ends the same simple way it began. With a body, in the dark, breathing slowly, held in place by the nearest, smallest, gentlest end of the very same force that shaped every single thing we have named tonight. That force has a name you have known since you were small. Gravity. And the smallest, gentlest thing it is doing anywhere in the whole universe tonight, it is doing to you right now, as the quiet weight that presses you softly down into your bed. Stay with what that actually means. The pull that reaches across 10 million light years to hold more than 80 galaxies together, that binds some 5 trillion suns, that draws the entire local group toward a single silent point out in the dark, does not switch to a different law when it arrives at you. It is one unbroken thread, with no edge anywhere along it. The same force that holds the giants on their long, slow orbits is the force holding you against the mattress. The largest thing you belong to, and the weight of your own body, are not two separate matters. They are the same force, only softer here, at the far, quiet end of its reach. And two things are happening to you as you lie here, and the gentle secret is that they are one and the same. You can feel the bed pressing up beneath you, carrying your weight, and that steady, soft pressure is gravity, doing its smallest work in the cosmos. But at the very same moment, you, and the bed, and the earth, and the sun, and the entire local group are all falling together toward that distant balance point we found tonight. And because every part of you falls at exactly the same rate, the fall makes no sensation at all. The stillness you feel right now is not the absence of motion. It is motion so complete and so perfectly shared that it has quietly become rest. You are falling, and you are still, and there is no difference between the two. That is not a soft way of speaking. It is the deepest thing we know about gravity. There is no experiment you could perform, lying here in the dark, that could tell you whether you are resting quietly on a bed or falling freely through empty space. Not similar. Identical. Einstein built his entire understanding of gravity on exactly that quiet fact, that falling and resting are, at the deepest level, the same state seen two ways. So the rest you feel tonight is not a lesser thing than all that cosmic motion. It is that motion, wearing its calmest face. Which means you do not have to hold yourself up tonight. You never did. The same force that carries 100 galaxies through the dark is carrying you, and it asks for nothing in return. You can let the bed take the whole of your weight. The falling will hold you, whether you keep watch over it or not. And look how much we came to understand together in this one quiet hour. That our home is far larger than it looks and built mostly of things no eye will ever see. That its truest edge is not a wall, but a still place where two great pulls fall silent against each other. That we are moving faster than we can picture in several directions at once and feel not a breath of it. That one distant day the sky will empty, and the very same gravity that carries every other galaxy beyond reach will keep our own home whole and lit and together for the rest of time. And that you were never a visitor to any of this. You were made here, out of local ash and the dust of vanished galaxies, and you are bound here and held here for as long as you exist. It might seem a strange place to fall asleep when you lay it out so plainly. A structure whose edge we only found within the last 100 years, whose weight we still cannot pin down better than a rough guess, filled with honest questions no one alive has answered yet. But the gravity never once waited for us to understand it. It held you last night, and every night of your life, and every night for billions of years before anyone knew the shape of any of this. Knowing the map does not change the holding. It only lets you rest inside it with your eyes open a moment longer, and then, when you are ready, closed. And when you do close them, none of it stops. The earth keeps turning slowly beneath you. The sun keeps carrying you along its great arc, the one that takes 230 million years to come around. The local group keeps falling, softly, toward the dark, exactly as it has since long before the earth was formed. The atoms stay gathered. The keel holds. Everything we name tonight goes on doing precisely what it does, faithfully, without needing you to watch over a single piece of it. You are allowed, now, to stop watching. Thank you for spending this hour here with me, out at the soft edge of sleep. Not for any algorithm, and not for any number. Only so that I know you were here, drifting through all of it beside me for a little while. That is a quiet gift, and I hold it gently. So let the rest of it go now. The 80 galaxies, the invisible mass, the empty pushing dark, the long unfelt fall, the edge made of nothing at all. Let it drift to the back of your mind, where it can keep you company without asking anything of you. There is only one piece of this whole vast story you need to keep as you go. The smallest gravity in it. The one that is with you right now. The weight of the blanket settling over you, warm and near and entirely yours, is the same field that shaped the giants and the ghosts and the whole long fall, arriving at last, soft and local and gentle, at the surface of your resting body. Let it hold you. Good night.